As one of the world's most polluted countries, with hundreds of millions of people still trapped in impoverished rural areas, India has transformed the enormous volume of coconut byproducts into construction materials for thousands of kilometers of roads, creating one of the world's most successful recycling models. So how did Indian engineers turn coconut byproducts into the foundation of sustainable roads? And why is nearly every part of the coconut utilized to build an industry worth billions of dollars? Join Agriculture Insight as we explore the story behind this remarkable achievement. Surrounded by more than 7,500 kilometers of coastline and blessed with a tropical climate, India has become one of the world's largest coconut-producing nations. Every year, the country harvests more than 21.4 billion coconuts, supporting the livelihoods of more than 12 million people and creating an industry worth billions of dollars. But behind this enormous scale lies a paradox. A coconut consists of a high-value edible kernel and a fibrous husk that accounts for a large share of its total weight. After processing, around 35 to 45% of each coconut remains as husk and fiber, and nearly 70% of that material is still not effectively utilized, generating an enormous volume of waste every year. Meanwhile, more than 60% of India's population still lives in rural areas, where thousands of kilometers of roads are repeatedly damaged by monsoon rains, flooding, and weak soil conditions. After just a few rainy seasons, many roads begin to sink, erode, or wash away, making it extremely difficult to transport agricultural products and maintain connections between communities. The intersection of these two challenges gave rise to an entirely new breakthrough. Instead of treating coconut fiber as waste, Indian engineers transformed it into geotextile mats that reinforce weak soil and prevent erosion. Under the PMGSY-3 program alone, approximately 10 million square meters of coconut geotextiles were used to construct 1,674 kilometers of roads across 7 states, marking one of the largest large-scale applications of coconut fiber in the world. To understand how the fibrous layer surrounding a coconut became the foundation of sustainable roads and a billion-dollar industry, we must begin with the process of harvesting billions of coconuts every year. A mature coconut tree typically stands between 15 and 30 meters tall, equivalent to a 5 to 10-story building, with a nearly vertical, smooth trunk and no branches to hold onto. As a result, in many traditional coconut growing regions, farmers still climb directly up the trunk using only the grip of their feet, a rope looped around their ankles, or simple climbing aids. A single slip from a height of dozens of meters can cause severe injury or even cost a person their life. For shorter trees, farmers use sickles attached to bamboo poles or alloy handles measuring approximately 6 to 9 meters in length to cut down each cluster of coconuts from the ground. This method is safer and faster, but it is only effective for trees that have not yet grown too tall. Once the trees exceed that reach, climbing to the top remains virtually the only option. After the coconut clusters, each weighing dozens of kilograms, are brought down to the ground, the process of sorting and removing the fibrous husk officially begins. In many traditional coconut growing regions of India, this work is still performed entirely by hand. Workers drive a sharp steel spike measuring approximately 30 to 50 centimeters into the ground, then use their full body weight to force each coconut onto the spike, tearing the husk into several pieces. Even a skilled worker can separate only about 60 to 100 coconuts per hour using this method. Once separated from the coconut kernel, tons of coconut husks are collected into massive piles and transported to coconut fiber processing facilities across India. There, what was once considered agricultural waste begins its transformation into one of the world's most widely used natural geotechnical materials. After arriving at the processing facility, the enormous piles of coconut husks enter the most critical stage of the entire process, extracting the coconut fiber. Instead of soaking the husks in water for several months as in the traditional method, most modern factories in India use decorticator systems to fully mechanize the process. The coconut husks are continuously fed onto conveyor belts and transported into crushing machines. Inside, rotating shafts equipped with dozens of steel blades and high-speed hammers continuously compress, crush, and tear apart the tough outer husks. The impact force breaks down the bonding tissues between the fibers and the coconut pith, releasing long fiber bundles without damaging their natural structure. The crushed material then passes through a system of vibrating screens and air blowers for separation. The long fibers are retained, while the coconut pith, dust, and smaller debris are separated out. From 1 ton of coconut husks, a processing facility typically produces around 250 to 300 kilograms of coconut fiber. The remaining material consists primarily of coconut pith and moisture, all of which is later utilized to produce growing media or organic fertilizer. With the ability to retain water up to approximately 8 times its own weight, along with excellent aeration and biodegradability, coconut pith is now widely used in vegetable farms, flower farms, and high-tech greenhouses around the world. The extracted fiber bundles still contain large amounts of dust and moisture. They are therefore thoroughly washed before being spread across drying yards covering thousands of square meters under natural sunlight. Throughout the drying process, workers continuously rake and turn the fibers to ensure moisture evaporates evenly while preventing the fibers from clumping together or developing mold. Only after the moisture content is reduced to 15 to 20% is the coconut fiber ready to move on to the heart of the entire coconut geotextile manufacturing process: carding and spinning. After reaching the required moisture level, the coconut fiber is fed into carding machines to remove short fibers, remaining dust, and align all the fibers in the same direction. This process makes the fiber bundles more uniform, softer, and ready for the spinning stage. Next, the fiber bundles pass through spinning machines, where multiple fine fibers are stretched and tightly twisted together into coir yarn of uniform thickness. The twisting speed and tension are continuously controlled to ensure the yarn has sufficient tensile strength to withstand heavy loads and outdoor conditions for many years. Every finished spool is inspected for diameter, tensile strength, and consistency before moving on to production. Only the spools that meet the required standards are transferred to the weaving system to produce geotextile mats used for soil reinforcement and erosion control. Using the coir yarn spools, the final stage begins on wide industrial weaving looms. Here, the yarns are woven perpendicular to one another in both the longitudinal and transverse directions, forming geotextile mats with mesh sizes and fiber densities carefully designed for specific applications. Depending on the project requirements, coconut fiber geotextiles typically weigh between approximately 400 and 900 grams per square meter, with a standard roll width of 2 meters and lengths ranging from 25 to 50 meters. These specifications determine the strength, soil retention capacity, and erosion resistance of each product. At this stage, these remarkable geotextile mats are ready to become natural reinforcement layers for roads and many other infrastructure projects. After the subgrade has been graded to the required design elevation, vibratory rollers and pneumatic tire rollers make multiple passes to compact the surface, creating a level, stable base that meets the specified density requirements before the reinforcement layer is installed. Once the roadbed has passed inspection, rolls of geogrid are transported to the construction site by truck, lifted into position using cranes or excavators, and distributed along the entire length of the construction corridor. Thanks to their relatively light weight, each roll can be pulled into position by several workers before being carefully aligned. The geotextile is then stretched to eliminate wrinkles and secured to the ground using steel stakes or bamboo stakes, typically driven into the soil at intervals of approximately 1 to 2 meters to prevent the mat from shifting during construction. At the joints, adjacent geotextile mats overlap by 20 to 30 centimeters, creating a continuous reinforcement layer across the entire road surface. Remarkably, constructing just 1 kilometer of rural road requires nearly 6,000 square meters of coconut fiber geotextiles. Once the entire geotextile system has been firmly secured, dump trucks begin placing the first foundation layer of sand, granular soil, or crushed stone over the surface. Instead of dumping the material into large piles, it is spread evenly in thin layers approximately 15 to 30 centimeters thick to avoid disturbing or damaging the coconut fiber geotextile beneath. Next, bulldozers and motor graders distribute the material evenly across the entire roadbed before multi-ton vibratory rollers compact it through multiple passes. Under the immense pressure, the soil and stone particles gradually fill the openings of the geotextile, creating a tightly bonded structure between the foundation layer and the natural ground beneath. Once the first foundation layer has been fully compacted and reaches the required design density, construction crews place the upper base layer using higher quality graded crushed stone. Finally, the road surface is completed with either asphalt concrete or cement concrete, depending on the requirements of each project. Throughout the lifespan of the road, the coconut fiber geotextile continues working beneath the pavement structure, reinforcing the foundation, reducing uneven settlement, and limiting erosion caused by rainwater. What makes this solution especially remarkable is that after approximately 3 to 5 years, once roadside vegetation has become well established and the soil has reached a stable condition, the coconut fiber gradually biodegrades, returning organic matter to the soil without leaving behind plastic waste like synthetic geotextiles. From a byproduct that was once discarded, coconut fiber has become the foundation of more than 1,500 kilometers of rural roads across India. This achievement has not only helped solve critical infrastructure challenges, but has also created a billion-dollar industry where agricultural waste is transformed into sustainable economic value. Yet that is only half the story. Beyond the coconut husk, millions of tons of coconut meat and coconut water also enter modern processing facilities, giving rise to a wide range of high-value products. The coconuts, with their fibrous husks already removed, are first sent through shell-splitting machines, where the hard outer shell is cut in half using rotary blades or hydraulic cutting systems. As soon as the shell is opened, the coconut water flows into stainless steel storage tanks through a closed collection system, minimizing contamination while preserving its natural flavor. The coconut meat attached to the inside of the shell is then separated using scraping machines or semi-automatic equipment. The white coconut meat is thoroughly washed to remove dust, shell fragments, and other impurities before being sorted according to its intended use. For coconut oil production, the coconut meat is cut into smaller pieces and fed into drying systems, where its moisture content is reduced from approximately 50% to less than 3%, producing copra, the standard raw material for oil extraction. Meanwhile, Factories producing desiccated coconut send the fresh coconut meat directly through crushing, steam blanching, hot air drying, and cooling lines before packaging. The coconut water is filtered through multiple stages to remove sediment before undergoing high-temperature, short-time pasteurization to eliminate microorganisms while preserving its natural taste. By utilizing nearly every part of the coconut, India has built a billion-dollar industry that supports the livelihoods of more than 12 million people and has established the country as one of the world's leading producers of coconut-based products. Thousands of kilometers of roads have been built from what was once considered waste. This is not only an achievement of India's coconut industry, but also proof that the solutions to some of the world's greatest challenges can sometimes be found in the very things people once dismissed as trash. Amid the massive ocean currents of the North Pacific exists a region containing trillions of pieces of plastic swirling endlessly for decades, covering an area of approximately 1.6 million kilometer squares, or roughly 3 times the size of France. And the world does not have just one, but as many as 5 gigantic ocean garbage patches like this. These are not solid floating islands of trash as many people imagine, but rather a plastic soup dispersed across an enormous area where ocean currents continuously gather plastic from all over the world. But the real danger does not lie in the massive pieces of plastic visible to the naked eye. It lies in the process by which they are continuously broken down by sunlight, ocean waves, and friction over many years until they become nearly invisible microplastics. These particles then enter the marine food chain and eventually return to the human body itself. In ecological logic, every year of delay in cleanup means all future intervention efforts become more complicated and expensive. But humanity delayed that process for more than 7 decades, ever since petroleum-based plastics began exploding on a global scale in the mid-20th century. Scientists estimate that this region accounts for only about 1% of the world's ocean water, yet contains up to 7% of all floating surface microplastics globally, equivalent to around 1.8 trillion pieces of plastic with a total mass reaching 100,000 tons. For many decades, experts almost unanimously agreed that cleaning this area was impossible. Estimated costs reached tens of billions of dollars, and using traditional methods such as ships and nets, the process could take thousands of years. But right in the middle of what seemed like a hopeless situation, a bold idea began to emerge. Instead of chasing plastic across millions of square kilometers of ocean, humanity would let the ocean currents themselves concentrate the waste in order to capture and transport it into massive industrial processing systems before it permanently degrades into microplastics. It was an approach that went against conventional intuition, yet perfectly aligned with the way the ocean itself operates. And to turn that seemingly irrational idea into reality, a 16-year-old Dutch boy named Boyan Slat emerged with an approach completely different from every ocean cleaning method that had existed before. 1 year after a disappointing diving trip off the coast of Greece, where he saw more floating plastic bags than fish, in the fall of 2012, at the age of 18, Boyan Slat stepped onto the TEDx Delft stage with an 11-minute talk titled, "How the Oceans Can Clean Themselves."
However, I believe the Great Pacific Garbage Patch can completely clean itself.
For months, Slat's seemingly naive question received almost no attention and gathered only around 2,000 views. But by February 2013, when technology and environmental media outlets began discovering it, everything changed almost overnight. Donations quickly started pouring in, forcing Slat to make the biggest decision of his life: continue pursuing his aerospace engineering degree or drop out of university to chase the ambition of cleaning the oceans. At the time, his bank account contained only around $300 in savings. Slat chose the ocean. Just days after the video went viral, the project received approximately $90,000 in donations. And by September 15, 2014, the total had reached $254,282, becoming the most successful non-profit crowdfunding campaign in history at that time. And from that moment on, in order to prove that the oceans could truly clean themselves, the Ocean Cleanup was officially born, with its first mission keeping millions of pounds of plastic stationary in the middle of the ocean. The Ocean Cleanup first had to solve an extremely complex physics problem: how to create a structure light enough to continuously float on the ocean surface, yet durable enough to withstand large waves, ultraviolet radiation, salt water, and mechanical stress for years in the open sea. The system's greatest distinction lay in its gigantic mechanical structure, designed as a U-shaped floating barrier approximately 600 meters long. To create this structure, the Ocean Cleanup used around 50 sections of high-density polyethylene pipe, each nearly 1.2 meters in diameter, a material commonly used in offshore oil and gas systems because of its corrosion resistance, impact durability, and ability to maintain stable buoyancy in harsh marine environments. Most importantly, the assembly joints were built using steel connectors, reinforced cables, and flexible linkages that allowed the entire structure to bend with the motion of the waves rather than resist them. Beneath the floating pipes, engineers installed a 3-meter-deep skirt made of technical fabric. This depth was carefully calculated to retain most plastic floating near the surface, while still allowing marine life to swim underneath, reducing the risk of harming the ecosystem. The operating principle of System 001 was based on a very small difference in movement speed between the system and the plastic waste. While floating plastic is pushed faster by wind and waves, Wilson generates greater hydrodynamic drag, causing it to move slightly slower and gradually funnel debris into the curved central section like a gigantic floating trap in the middle of the ocean. In September 2018, System 001, nicknamed Wilson, was officially towed out of San Francisco Bay to begin its first real-world test in the largest garbage patch on Earth. However, the system quickly revealed serious limitations. Unstable ocean currents and inconsistent drifting speeds prevented the system from keeping plastic concentrated inside the barrier, causing much of the debris to escape back into the ocean instead of remaining trapped for collection. By the end of 2018, an 18-meter section fractured due to material fatigue at welded connection points, forcing the system to be towed back to Hawaii after collecting only around 4,000 pounds of plastic in 4 months. The figure was far below initial expectations. As a result, System 001B was introduced in 2019, an upgraded version designed specifically to solve the problems that had caused Wilson to fail. Beneath the system, a parachute-style floating anchor approximately 6 meters long creates additional hydrodynamic drag, allowing the entire structure to move about 0.3 to 0.5 meters per second, slower than the floating plastic on the surface. This very small speed difference is enough for tens of thousands of plastic fragments to continuously accumulate in the central area, while retaining thousands of pounds of waste during each collection cycle. After around 6 to 8 weeks of operation at sea, the plastic accumulated in the center of the system is lifted onto the support vessel using industrial cranes. On the ship's deck, workers begin preliminary sorting of fishing nets, hard plastics, large containers, and organic contaminants before all the plastic is packed into containers and transported to recycling facilities. This process is extremely difficult because much of the plastic has drifted through the ocean for years, exposed to saltwater, UV radiation, and marine organisms that degrade and contaminate the material, making sorting and recycling far more complex than conventional land-based plastic waste. Its composition is also astonishing. Fishing nets account for 46% of the total mass, while between 75% and 86% of the plastic originates from offshore fishing activities. After more than 10 upgraded versions since System 001 Wilson, by 2025, the ocean cleanup had removed more than 25,000 tons of plastic waste from river systems and oceans worldwide, equivalent to the mass of tens of thousands of gigantic Labubu figures being pulled back out of the sea. But the ocean cleanup quickly realized that cleaning the oceans alone was not enough, because around 1,000 rivers, representing less than 1% of the world's river systems, are responsible for nearly 80% of the plastic continuously flowing into the oceans every year. Among them, Thailand, China, Indonesia, the Philippines, and Vietnam alone release as much ocean plastic as the rest of the world combined. This discovery changed the nature of the problem itself. Instead of focusing solely on cleaning up plastic that had already drifted into the ocean and dispersed across millions of square kilometers, the organization shifted toward a strategy of intercepting plastic at highly concentrated entry points, where river flow and geometry allow for far more efficient intervention in terms of energy and cost. From this logic, the Interceptor system was developed as an automated river plastic collection platform. Each system is approximately 24 meters long, nearly 16 meters wide, and permanently anchored along riverbanks using heavy-duty piles and tension cable systems. Extending from the Interceptor's main body, a floating barrier stretching dozens of meters is positioned diagonally along the direction of the current to continuously guide floating waste toward the central intake opening. As debris approaches the system, an automated conveyor belt approximately 1.5 meters wide begins operating, continuously lifting plastic from the water surface into the vessel. The entire system operates on solar energy, using around 32 solar panels installed on the roof to power the conveyor belts, sensors, and AI systems that monitor waste flow in real time. One of the most notable projects in the United States is Interceptor 007, deployed on the Los Angeles River, one of the most plastic-polluted urban rivers in America, where more than 220,000 pounds of waste were intercepted within the first months of operation before reaching the Pacific Ocean. But pulling millions of pounds of plastic back out of rivers and oceans was only the beginning. The next challenge was how to transform that chaotic mass of waste into reusable industrial raw materials on a massive scale. As soon as the material is brought back to land, the entire volume begins undergoing a careful sorting process based on polymer type, aging level, and recyclability. In reality, around 80% of the collected plastic has deteriorated and become contaminated to the point where it is no longer suitable for commercial recycling. This portion is typically processed through energy recovery systems or strictly controlled destruction methods to permanently remove it from the environment, instead of allowing it to continue breaking down into microplastics in the ocean. Only around 20% of the plastic remains stable enough to proceed into material regeneration lines. This mainly includes hard plastics, HDPE, polypropylene, and especially nylon fishing nets with lower levels of degradation. After being separated, the plastic continues through large high-pressure washing tanks to remove salt, sand, oil, and attached marine organisms before being fed into high-speed industrial shredders. Here, the material is cut into fragments several centimeters in size before continuing through polymer separation systems using optical sensors and float sink density sorting. plastic that meets final quality standards is then melted at temperatures of approximately 180 to 280 degrees Celsius inside industrial extruders, before being stretched into strands and cut into small recycled plastic pellets. Because of the extremely high costs of collection, transportation, and processing, ocean recycled plastic is often sold at prices up to 5 times higher than conventional recycled plastic, ranging from around $2,000 to more than $5,000 per ton, depending on material quality and purity. These plastic pellets are then sold back to manufacturers to produce sunglasses, packaging, electronic components, furniture, and many commercial products labeled as ocean recycled plastic. Some recycled ocean plastic has now even begun appearing in globally distributed commercial products. Coldplay once partnered to use plastic collected from rivers and oceans to produce recycled vinyl editions for one of their album releases, while Kia also partnered with the Ocean Cleanup to integrate recycled ocean plastic into next-generation automotive interior components. From a teenager standing in front of floating plastic bags in the Mediterranean, humanity has now, for the first time in history, begun truly addressing ocean pollution on a massive scale, proving that what was once considered impossible is sometimes simply a problem that has not yet been approached with the right way of thinking. By mid-2026, the Ocean Cleanup had removed more than 110 million pounds of plastic waste from rivers and oceans, operating 21 interceptor systems across 10 countries, with a team of around 200 employees from all over the world. The estimated cost of completely cleaning the Great Pacific Garbage Patch is $7.5 billion over 10 years, and the mission remains unchanged, removing 90% of floating ocean plastic by 2040. Even so, the amount of ocean plastic currently collected and recycled still accounts for less than 1% of the global plastic recycling industry, while the world continues producing more than 400 million tons of new plastic every year. And as plastic continues flowing into the oceans every single day, this battle has perhaps only just begun. In your opinion, what is more dangerous? The millions of tons of plastic already floating in the oceans, or humanity continuing to produce more of it every day? Plastic is not the only material that modern civilization is learning how to regenerate, because every year hundreds of billions of glass bottles are also entering one of the most complex industrial recycling systems in the world. So how do thrown-away garments manage to embark on a journey of rebirth and return to store shelves? It begins at collection centers around the world, where heaps of used clothing are transported to large-scale recycling facilities. There, AI systems and workers sort them by material type and fiber structure. From there, the fabrics are cut into pieces, shredded into fibers, or chemically processed to extract raw materials. These materials are then spun into yarn, woven, and dyed once again, creating a new generation of textiles for the global fashion industry. Right now, let's join Agriculture Insight to explore how the fashion industry is attempting to transform one of the world's largest waste streams into the future of itself. Although it is widely seen as a solution to the fashion waste crisis, textile recycling is far from simple in practice. Many garments must go through a series of complex processes such as fiber shredding, chemical separation, cleaning, and re-dyeing, consuming enormous amounts of electricity, water, and energy. This becomes especially challenging with blended fabrics like cotton polyester, where separating individual fibers is far more complicated than recycling plastic or paper. Despite the enormous costs, the global textile recycling industry is still growing at an extraordinary pace. From recycled fibers and secondhand clothing to used garment exports and industrial materials, millions of tons of discarded textiles each year are generating tens of billions of dollars in value. This has driven countries such as China, India, and Sweden into a competitive race to develop recycling systems, treating it like the extraction of a new resource mine. Beyond traditional recycling, many brands are also embracing the trend of upcycling, transforming old garments into unique, high-value fashion pieces. From jackets made of reclaimed denim to handbags assembled from fabric scraps, what was once considered waste is now appearing on fashion runways and being sold at premium prices. It all begins with clothing donation bins placed in residential areas, shopping centers, and fashion stores around the world. Every day, tons of used garments are brought by people and dropped into these collection points instead of being thrown directly into landfills. Once the bins are full, specialized trucks continuously transport the collected clothing to large-scale processing centers. There, the items are first weighed and roughly inspected to separate those that are still wearable. Pieces that are too old, faded, or damaged are then sent onward to advanced recycling facilities. After the initial sorting process is completed, the remaining clothing is fed into massive hydraulic presses, where they are compressed into bales weighing hundreds of kilograms. These bales are then transported to specialized recycling plants, where the journey of transforming fashion waste into new raw materials truly begins. For items that are still in good usable condition, they enter the global secondhand clothing industry. After being cleaned, sorted, and packed, millions of tons of used garments from the United States and Europe are shipped in containers to Africa and Southeast Asia, regions where the demand for affordable clothing remains extremely high. Upon arrival, these bales of secondhand clothing, each weighing hundreds of kilograms, are delivered to massive used clothing markets, where tens of thousands of items are bought and sold every day. From t-shirts costing only a few tens of thousands of dong to vintage jeans and branded jackets, countless pieces that might otherwise have been discarded continue their life cycle instead of ending up as waste. Some shipments are even sold as mystery bales, meaning buyers have no idea what is inside until the package is opened. This treasure hunt experience has fueled the rapid growth of the secondhand market, especially among young consumers who are drawn to vintage styles and unique fashion pieces. But behind this bustling secondhand market, millions of tons of used clothing are still waiting to enter massive recycling facilities. There, they begin the most critical stage of the entire process: sorting. Inside these modern factories, artificial intelligence, color scanning cameras, and infrared sensors continuously analyze every garment moving along high-speed conveyor belts. Within just a few seconds, the system can identify fiber types such as cotton, polyester, wool, nylon, or denim, before automatically blowing each item into its designated processing stream. Alongside AI systems, hundreds of workers must still operate in constant coordination to check colors, fabric thickness, damage levels, and other details that machines may overlook. Because even a small amount of incorrectly mixed material can significantly reduce the quality of the entire recycled batch. This is also why textile recycling is far more complex than recycling paper or plastic. Most modern garments are made from blended fibers designed to improve elasticity, durability, and reduce production costs, making the separation of individual materials extremely difficult. After sorting is completed, used clothing moves on to the shredding and fiber separation stage. At this point, tons of fabric are cut into smaller pieces by massive industrial blade systems, before being fed into high-speed shredders that break down the original fiber structure. In a short time, old t-shirts, jeans, and jackets are transformed into a thick, cotton-like mass of fibrous material. This becomes the key raw input for the next stages of recycling inside the plant. However, with each recycling cycle, textile fibers become significantly shorter and weaker compared to their original state. This also means clothing cannot be recycled indefinitely, as repeated processing eventually reduces fiber quality to a level that is no longer strong enough to produce new garments. For this reason, many factories often need to blend in virgin fibers to the recycled material in order to maintain the durability of the final products. After the shredding stage, the resulting fiber mass is sent to a cleaning system designed to remove dust, loose threads, zippers, buttons, and any remaining contaminants within the fiber blend. In many modern facilities, industrial magnets, high-pressure airstreams, and automated filtration systems operate continuously to separate metals and other unwanted materials from the textile fibers. For certain garments made from heavily blended materials, the process becomes even more complex, as they may require chemical treatments to separate individual fiber types before recycling can continue. This is also considered one of the most complex and energy-intensive stages in the entire textile recycling process. After cleaning, the fiber mass is sent to the spinning stage, where piles of discarded clothing gradually begin to return to the form of a completely new raw material. Since the fibers produced after shredding often retain the original color of the fabric, many factories can directly take advantage of tones such as black, gray, or denim blue without the need for full re-dyeing. This significantly reduces water usage, chemical consumption, and energy demand throughout the recycling process. Meanwhile, white textiles are considered the most versatile material in the recycling industry, as they can be dyed into almost any color afterward. For this reason, white fabrics are often more valuable and are carefully separated from the very beginning of the sorting process. After the spinning process is completed, the massive rolls of recycled yarn are transferred to weaving factories, where they are transformed back into finished fabrics. At this stage, thousands of threads are interlaced by high-speed industrial looms, producing continuous rolls of fabric for the fashion industry. Depending on the type of fiber and weaving technique, these recycled textiles can be turned into t-shirts, hoodies, towels, or even various industrial materials. However, denim is considered one of the most distinctive materials in textile recycling. Unlike many other fabrics, used jeans often retain their characteristic indigo blue color even after being shredded and respun into new fibers. As a result, many factories can continue weaving them into new denim without extensive re-dyeing. On specialized weaving machines, thousands of blue threads are continuously interlaced to recreate the thick, durable structure typical of denim fabric. This ability to preserve its original color has made recycled denim one of the most important directions in sustainable fashion, especially considering that producing a single new pair of jeans can consume thousands of liters of water. For white or very light-colored fabrics, they are typically sent to the dyeing and finishing stage. This is where recycled fabric rolls begin to take on a completely new appearance before returning to the fashion industry. Inside the factory, massive rolls of fabric continuously pass through industrial dyeing systems stretching tens of meters long, where dyes are deeply absorbed into each fiber under carefully controlled temperature and pressure conditions. Depending on the final product, the fabric may then undergo additional treatments to enhance softness, improve elasticity, reduce wrinkling, or create various surface effects. Once completed, these recycled fabric rolls are cut, sewn, and transformed into a wide range of new products, such as t-shirts, hoodies, handbags, and fashion garments, completing the journey of turning once discarded clothing into entirely new creations. For recycled denim, the journey does not end after it has been woven into fabric. The newly produced denim rolls are then sent to the finishing stage, where they gradually take the shape of familiar jeans seen in the market. At this stage, the fabric is cut, sewn, and surface treated to create faded effects, distressed textures, or signature vintage styles. Many modern factories even use laser technology to etch patterns and create highly precise fading details on the surface of the jeans. Once completed, these recycled denim products continue to appear in fashion stores around the world, where few people realize that they once began as discarded pairs of jeans dropped into donation bins. However, despite the rapid growth of the textile recycling industry, the global volume of discarded clothing continues to rise at an enormous pace. One of the biggest driving forces behind this trend is the explosion of fast fashion. With brands such as Shein, Zara, and H&M, new collections are released every few weeks, fueling a non-stop cycle of consumption. Low prices, TikTok trends, haul videos, and micro-trends have made wear once culture increasingly common. People buy clothes just for photos, viral trends, or short-lived bursts of excitement. This pace of consumption is creating unprecedented environmental pressure. Polyester clothing, when washed, can release thousands of microscopic plastic fibers into rivers and oceans, making it one of the largest sources of microplastic pollution today. At the same time, industrial dyeing processes discharge vast amounts of wastewater containing toxic chemicals and heavy metals. All of this combines into a single outcome. Millions of tons of clothing are discarded every year, turning many regions of the world into massive fashion graveyards that far exceed the capacity of current waste management systems. A striking example is the Atacama Desert in Chile, considered one of the world's largest dumping grounds for discarded clothing, or Contamonto Market in Ghana, a massive second-hand hub in West Africa, where continuous inflows of used garments eventually still end up as waste. As the problem continues to intensify, the fashion industry has begun exploring a completely different direction, turning to nature as a new source of materials for the future. From bamboo fibers, seaweed, and mycelium fungi to pineapple leaf fiber, hemp, and fruit byproducts, materials once considered waste are now being tested to create new types of textiles. However, in reality, these materials are still far from mainstream adoption. The vast majority of clothing today is still produced from cotton and polyester, the two dominant fibers in the global fashion industry. As a result, so-called eco-friendly materials currently play a supporting role rather than serving as a full replacement. From discarded garments that once seemed worthless, textile recycling technology is opening a new life cycle for fashion, where waste does not disappear, but is reborn into new products, continuing to circulate within the ever-evolving world of fashion. A little-known fact: most clothing in the world is not made from natural fibers, but from plastic, primarily polyester, which accounts for about 70% of the global market. More strikingly, the raw material for this fiber often begins as discarded plastic bottles. Before being transformed into fabric, plastic must pass through the sorting stage, a critical step that determines the overall quality of the output. Although there are theoretically 7 recycling codes, in practice only PET and HDPE are clean and valuable enough to be reprocessed. In modern facilities, rotating drums, screening systems, and optical sorting robots work together to remove dirt and impurities, accurately separating materials with high efficiency. The selected plastic bottles are then shredded into small flakes, thoroughly washed, and processed through float sink separation to eliminate unsuitable materials. These flakes are melted, filtered through ultrafine screens, and cut into millions of plastic pellets per hour, an intermediate raw material used across various industries. From here, the pellets are reheated and extruded through spinnerets with microscopic holes, forming filaments finer than human hair. These fibers are rapidly cooled, stretched to enhance strength, and wound into yarn, serving as the foundation for polyester fabrics found in clothing, backpacks, and countless consumer products. The entire process represents a remarkable transformation, turning plastic waste into high-value textile material. However, its downside is becoming increasingly evident. During use, especially when washed, polyester fabrics release microscopic plastic particles into wastewater, which eventually flow into rivers and oceans and ultimately return to the human food chain, raising significant concerns about the true sustainability of the industry.